9.5, so we are still looking at absorption of materials. In particular, we are now looking at the capillary network and where we do the exchange. And we're not going to look at all exchange surfaces, we're going to look at the main two that you need to know for the content. So what do we mean by an exchange surface? So an exchange surface is somewhere where we have the blood is close enough to the tissue that it needs to exchange it with. So that means like the body cells. So you should already know what this one is. Our main exchange surface that we're talking about is the capillary network, because it spreads through every tissue and it's close enough that you can get diffusion into and out of the blood. This is a micrograph showing it spreading through everything. To make a good surface for exchange, what we need is something that's good for diffusion, because this is how you do exchange. So diffusion, you should already know. Straight definition, movement of particles from an area of high concentration to an area of low concentration. You might see a movement of molecules from an area of high concentration to an area of low concentration. The essential thing is it's high to low. Okay, so we have a high concentration piled up of a particular compound, and then we've got a low on the other side, and because of that it runs down the hill. Okay, passive transport, key area 2 from cell biology. So anything at all that makes a good concentration gradient, so keeps this, so if I could pile this up even higher, that would help because it's a steeper slope. If this gets low though, so if I lose some of these guys, so if these ones go down, then my concentration gradient is much less, it's less steep, and so that'll slow it down. So either I need to keep this up high, or I need to keep this going away. So every time I remove these, then this would also make it steeper. So you can, either of those would be good, okay? So the surfaces that are good for this have particular features that you need to know. The three things that you need to be able to give for this one. So the first is a large surface area, and that's kind of obvious because if you try and hit something, if you've got a particle that needs to hit something, the bigger the area is going to make it better. So say this was a wall and here's your target that you're trying to throw something at, throw a ball or something at it. If I make the target the whole size of the entire wall, it suddenly makes it a lot easier. So if I can take something which was a single surface and fit that in a smaller space, so what I do is basically fold it and I do that to it, now I can get to all of these surfaces and it's taking up less space than it was when it was flat, and you can actually put more and more of it in, which is what we do, and we do it really well. Thin walls, again, kind of obvious. If you have something that is only one cell thick, it's going to be much easier to pass something through it. So that's what we go for, one cell thick. Anything thinner than that wouldn't be a surface because no cells. And finally, a good transport system. Now that one's not quite as easy, but it is one that should hopefully make sense. It's the idea of this concentration gradient. So if I've got something which is constantly taking away anything that moves across, so again, if I've got here's my high and here's my low, okay, and so this one falls over here, so this stacks up to 2, but I then take that one straight away, then this is back down to 1 again. So it keeps this as high as it possibly can. So anything that keeps on putting more stuff in on the high side or takes more stuff out on the low side, that's good. So things to look out for. Any of them, those three, gives you efficient exchange. And the two things that we're going to look at are the alveoli in the lungs and the villi in the small intestine. The villi is the villi, you're not going to be able to call it anything else, but you can absolutely call these air sacs. And we will use those interchangeably.